Hi, everyone. Welcome to this fourth lecture in the practical introduction to quantum computing here at CERN. And first of all, I would like to apologize because we have experienced some technical problems with uploading the recording of the third lecture to YouTube. You know that it is available on CDS, on the CERN document server, and you can watch the recording there. The link is on the Indico page for the third lecture. And we will eventually upload also the recording to YouTube. Some of you prefer to use that platform, but it will experience some delay. So sorry about that. We are working on solving the problems, and we will try to upload the video for the third lecture and also for this fourth lecture as soon as possible, okay? As always, I would like to start by answering some of the questions that we have received about the content of the previous lectures. And there is one that was quite popular. Some people asked about this. Also, some people asked about solving some of the exercises that I have proposed. So I'm going to give you the solution to one question or one small exercise that I proposed last week. Okay, so you should be now seeing my slides on the possibility of trying to attack the BB884 protocol for quantum key distribution by using entanglement. Okay, when we studied BB84 on the second lecture, we had not yet studied entanglement, but then on the third lecture, I suggested that maybe if could try to use this property in order to learn something about the qubit that Alice is sending to Bob, okay? So let's imagine that in the protocol, Alice sends the qubit, which is coded in one of the bases, either the 0-1 basis or the plus-minus basis to Bob, and then Alice intercepts this qubit and tries to do the following. We studied when we first talked about the BB884 protocol, the possibility of Alice measuring the qubit and then resending something to Bob. But now what she tries to do is to use another qubit, which is in 0 state, and with the CNOT gate entangling the qubit that Alice is sending to Bob, what I'm calling here psi, with her own qubit, okay? So she entangles this qubit that she has intercepted with one of her own, and then she sends the original qubit without doing anything else to it to Bob, okay? And then she waits until Alice and Bob reveal the basis of measurement, and then she uses that same basis to measure her own qubit, okay? So this is a possible attack. When one learns about quantum entanglement, one can think that this is something that it could use to learn something about psi. And in fact, it works if the qubit is either 0 or 1. Okay, you can just compute the different states, and you will see that in that case, Alice will completely get the information about psi if it is either 0 or 1. But remember that randomly, Alice can also choose to encode her information, her bit, in the plus-minus basis. She does not always send the qubit in the 0-1 basis, which would be equivalent to sending it as classical information, but she also uses this conjugate coding in order to send the information in a different basis. So imagine that instead of 0 or 1, Alice is sending this qubit psi, which is in state plus. Then what Eve does, she cannot know without measuring what is the qubit, and even if she measures, she cannot recover complete information about the qubit. So she needs to use the CNOT gate as before, and then the state of the two qubits, of the qubit that Alice is sending to Bob, and of the qubit that if is using to entangle, will be this Bell pair here. Okay, this is exactly what we have done several times in the previous lecture. Okay, so now she sends the first of these qubits to Bob. Okay, this is the qubit that she had intercepted, so she resends this qubit to Bob. And then Bob receives this qubit, and he can decide to either measure in the 0-1 basis or in the plus-minus basis. If Alice sends this qubit, if Bob measures this qubit in the 0-1 basis, then this is an incorrect choice, and this bit will be discarded. It won't be used for the key generation. Okay, so we can just simply ignore that situation. The interesting situation is when Bob uses the plus-minus basis to measure. In that case, remember that what he has to do is to apply the Hadamard gate, and then he has to measure. But if he applies the Hadamard gate to this state, which is now entangled with Eve's qubit, you can easily check that then the state of the whole system of the two qubits after Bob applies the H gate is this one here, okay? And now he has to measure the first qubit, the qubit that he has received. But notice that he has 50% probability of obtaining 0 if he measures this first qubit of this state. Oh, sorry, there is a problem here. This should be 1, 0. Sorry about that. I will correct it and upload the new version after the lecture, but this should be 1, 0. And then he has 50% probability of measuring 0 and 50% probability of measuring 1. But this is not what should happen, because if Eve had not entangled the qubit, then since Bob is using the same basis that Alice was using for encoding the bit, he should recover exactly the bit sent by Alice. So in this situation, half of the time he will obtain an incorrect answer. And if Alice and Bob share some of the bits in the key to check whether everything is going correctly, they will notice that there is some interaction with their qubits, probably because of an external agent. Okay, so this is why this protocol does not work. Also, you can check that something similar happens with if Alice sends the minus state. And in that case, Alice and Bob can again detect that there is some eavesdropping on the line. And this is why this simple attack, there are more complicated attacks, cannot work. Okay, so let me use my headphones because there is some noise from the computer and maybe it's better to do it this way. Okay, so this was the first question, or one of the most popular ones. There was another question about what happens in the quantum teleportation protocol. In the quantum teleportation protocol, remember that we start by supposing that Alice and Bob are sharing an entangled pair, exactly one like this one here, a Bell pair, okay? And some people have asked how they can get this entangled pair if they are supposed to not have a quantum communication channel through which they can send these qubits, okay? So the idea here is that maybe they have met in the past and they have prepared in advance some entangled qubits, and then they have split the qubits and they have kept half of them. Or maybe there is a third party which can send Alice and Bob part of an entangled pair. Okay, this is something that also can happen without needing to have a communication, a full communication channel between quantum communication channel between Alice and Bob. Okay, so I hope this answers the question. And there was another one about the evaluation of functions with the Oracle, but since we are going to deal a lot with that today, I will answer that question later. Okay, so I think that's more or less all about the most frequent questions received this week. I again thank you for the interest and for all your feedback, and please feel free to keep on sending questions by email. The people who are joining us on the Zoom channel, please feel free to ask questions at any time. I will be very happy to answer any doubt that you may have. Okay, so now let me change my slides to the ones that we are going to use today. Just let me, please allow me a minute to select the correct file. Okay. Okay, so up to this point, we have been working only with systems of 1, 2, or even 3 qubits in the case of quantum teleportation, but this does not exploit at all the full capacity of quantum computers. The full capacity of quantum computers comes into the limelight when we use systems with many qubits. Okay, so this is what we are going to start studying today and in the rest of the lectures of the course. And in fact, you may think that, well, this is going to be much more complicated than what we have studied so far. But in fact, this is just a simple generalization of what we have been doing. Okay, so we have come, in fact, a very far way in the study of quantum information and quantum computing, and we only need to apply these notions that we have already studied for 1 qubit, for 2 qubit systems, to a situation in which we have many qubits. Okay, so now imagine that we have n qubits. N can be a big number, and as we know, each of the individual qubits can be in state 0 or in state 1. Okay, so the combination of all the n qubits can be in state 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, all the possible 2 to the m possibilities of zeros and ones. Okay, this is sometimes difficult to write or to work with, to explicitly write all the bits in the string. So we simply write sometimes just 0, 1, 2, 3, 2, up to 2 to the n minus 1, the binary number that is represented by the binary string. Okay, so this is a way of working with this in a more compact notation. Okay, so we can have the whole state of the n qubits in state 0, in state 1, in state 2, up to state 2 to the power n minus 1. And of course, we can have superpositions of those states. This is something that we have seen in 1 qubit systems, in 2 qubit systems. Of course, in n qubit systems, we can have a superposition of all the basic states. And in this case, of course, we are going to have a linear combination with complex coefficients of the different possibilities for the individual qubits combined in these basic states. And we know that for this to have physical meaning, for this to be something that is a real state of an n qubit system, we need this normalization condition. We need that the amplitude squared of the different possibilities add up to 1. Okay, and you know that this is a condition that we need because when we measure the system, we are going to obtain, imagine that we measure all the n qubits at the same time. So we are going to obtain one of the basic states. We are going to obtain either 0, 0, 0, 0, 0, 0, 0, 1, one of these states, okay? And the probability of obtaining one of these states is exactly the amplitude squared of that state in the superposition that is the general state. And after this measurement, you know that we have the wave function collapse, and now we have this state that we have measured. We do not have a superposition anymore. This is exactly what we had with 1 qubit systems, with 2 qubit systems, but now we have 2 to the n possibilities. And this is something that we are going to use in our favor when we study different quantum algorithms. We are here working with using 2 to the n, an exponential number of coefficients of amplitudes, and we have an exponential potential of managing information with these states of n qubit systems. Okay. We can, of course, measure the n qubit system, all the qubits at the time, but we can also measure just some of the qubits. Okay, so imagine that we have this superposition, this general state for an n qubit system, and we measure just one of the qubits. In this case, I'm measuring the one that is in position J, but you can measure the first or the last, whatever you want. Okay, what will we obtain? Well, we will obtain either 0 or 1. When we measure 1 qubit, we always obtain either 0 or 1. And the probability of measuring 0 comes from, of course, the amplitudes of those states in the linear superposition that have a 0 in the position J. Okay, so I'm calling all those numbers I sub 0 here. And what we need to do in order to obtain the probability of measuring 0 on that particular qubit is to compute the absolute value of the amplitudes, to square that value, and to add up all those amplitudes squared. Okay, so what we have is the sum of the probability of obtaining one state with 0 in that position, or another different state with 0 in that position. And we do this for all the different possibilities that are consistent with measuring 0 in that position. Okay, now the state will collapse to a superposition of all those possibilities which are compatible with having a 0 in the position J. And that is exactly this sum here, and we need to normalize by this factor in order to have something that satisfies the normalization condition. Okay, so this is exactly the same that we did with 1 qubit, with 2 qubits, but now it's more general. The formulas may look a little bit more complicated, but it's exactly the same idea. Okay, so far nothing new. We only have the same concepts, but now with n qubits. Okay, what about, this is for the general representation of the system, for the measurement either with all the qubits or with just one. What about the transformations? What about the quantum gates? Well, of course, if we have an n qubit state, we can, as always, represent this as a column vector. In this case, we are going to have 2 to the n coefficients, but again, we have a vector. And then the transformations need to be matrices of size 2 to the n times 2 to the m, unitary matrices to keep the normalization condition on the state of the qubits. And these are going to be the operations that we can do with the n qubit state. Okay. Also remember that when we have the n qubit state represented in this Dirac notation, we can easily compute the inner product, because we know that all the states in the basis are orthonormal. Okay, they satisfy this condition here. If I is different from J, then this product is going to be 0. If I is equal to J, then this product is going to be 1. So this is the usual notation with the Kronecker delta. Okay, so if we have a state of this form, we can easily compute the inner product with another state also in Dirac notation by using this fact here. Okay, so if you remember the previous lectures, at this point, what we did was to study different quantum gates for either the 1-qubit systems or for the 2-qubit systems. So you can imagine that now we are going to introduce a lot of gates, a lot of quantum gates for the general situation, for n qubits. Well, in fact, we are going to introduce at least one gate which works with more than 1 qubit. But you will notice that, in fact, the work that we have been doing so far is enough to know what happens with these n-qubit systems with already the quantum gates that we have studied. We don't need to introduce many more new operations or transformations, okay? What I really want to do is to introduce at least the Toffoli gate, which is a very important gate, which is a gate that we are going to use in some of the examples that we are going to run today, okay? And this is also important because it has properties that makes it relevant, for instance, to study what we call universality of quantum gates and classical gates that we will explain in a minute, okay? So what is this Toffoli gate? This Toffoli gate is also called a doubly controlled NOT gate or a CC NOT gate. The CC comes from control NOT gate, okay? And the idea is that we have 3 qubits. It acts on 3 qubits. The first two, the top ones, X and Y here, are the controls, okay? And Z is going to be the target of the gate, okay? So what happens is if both X and Y are 1, then we are going to flip the value of Z. This is exactly what we had in the case of the CNOT gate, the 2-qubit gate that we studied previously in the previous lectures. But now we have 2 controls instead of 1. Both X and Y need to be 1 in order to flip, to apply the NOT gate to Z. And we can express this as this logical formula, this Boolean formula here. This is the XOR, and we are going to add to Z with this XOR the conjunction of both X and Y. Remember that this is the AND, the logical, the classical AND gate. So this is going to be 1 if both X and Y are 1, and it's going to be 0 if either X is 0 or Y is 0. So we are going to XOR Z with 0 when at least one of X or Y is 0, and we are going to XOR Z with 1 when both X and Y are 1. Okay, so what we are doing is exactly what we said before. We are flipping the value of Z only if X and Y are both 1, okay? And this is an important gate because with this gate, we can construct any classical circuit that you can do with classical gates, with the AND gate, with the OR gate, with the NOT gate, and all those gates that you know from digital computing, okay? Why is it the case? Well, it's very easy to see because notice that what we are computing here, in fact, if we set this bit set to 1, is the NAND, the negation of the AND of X and Y. If I set this to 1, we can compute the NAND of X and Y. And we know that in classical logic, NAND is a universal gate. If we can implement the NAND gate, then with only that gate, we can implement any Boolean function, okay? So we can use the Toffoli gate to construct a NAND gate, a reversible NAND gate, and then we can use that NAND gate to construct any Boolean circuit that you need, okay? So this makes this gate very important because it shows that quantum computing is at least as powerful as classical computing, because we can reproduce any circuit that we have with classical logic, okay? However, this Toffoli gate by itself is not universal for quantum computing. It's not something that we can use to construct any other possible gate. You can easily see this because, in fact, if you compute the unitary matrix for this gate, you will notice that the coefficients are always zeros and ones. So you cannot obtain some of the gates that we have seen so far, like the rotation gates, which have complex coefficients. Okay, so this is not enough for universal quantum computing. And in fact, we don't even need to include this 3-qubit gate or any other 3 or higher qubit gate. Okay, this is a very interesting result and a very important result, which is somehow the basis of the possibility of doing quantum computing in practice. And the idea is that with only a subset of gates, we can construct any other possible operation. Okay, so when we have an n-qubit system, in fact, in principle, we have to use matrices which are of size 2 to the n times 2 to the n. Okay, but we can decompose these matrices by means of the unitary transformations for 1 qubit and 2 qubits that we have already studied. This is what we call universality of sets of gates. We need to clarify something here, especially for the mathematicians in the audience, because of course it's easy to see that the number of unitary transformations that you can conduct on a system of n qubits for n general n is non-numerable. Okay, so this is cardinality of the same size as the real numbers. Okay, so if we try to generate all these possible transformations with a finite set, this is impossible, because with a finite set, at most we can obtain an infinite numerable number of gates. Okay, what we are talking about when we talk about universality in this sense in quantum computing is about the possibility of approximating any possible transformation up to the precision that we need. Okay, so what we are saying is that we are just fixing a finite set of gates, and we are going to approximate all the other gates. Okay, technically what we have here is a topological property that we call density. So the set of gates that we can generate with this finite set is dense on the whole set of gates. Okay, I'm not going to give you the full proof of these statements. You can find proofs, very interesting and I think very readable proofs of these facts on both the Qiskit textbook that I have linked on the recommended resources, and also on the book by Nielsen and Chuang. In the book by Nielsen and Chuang, you have more details, but I think that if you want to feel the taste of the proof, if you read the chapter on the Qiskit textbook, that is more than enough to see what is going on. Okay, and then what we can prove with these techniques is that with just the 1 qubit gates that we have studied so far, the rotations that we studied on the first and second lectures, and the CNOT gate, then we can approximate any other gate to the precision that we need. Okay, and in fact, we can go even further, and we can prove that with just the NOT gate, the Hadamard gate, the T gate, and the CNOT gate, we can approximate all the other gates, no matter how many qubits we have. Of course, the number of times that we need to use these gates can grow exponentially, but we can do it in principle. We can approximate any transformation on any number of qubits that you need. Okay, as I said, I'm not going to prove this in detail, but at least I want you to see some of the equivalences that we can use, at least to prove that with these NOT, Hadamard, and T gates, we can generate some of the other gates that we have been studying. Okay, so for instance, This is something that you can check easily, each of these equivalences, either by computing the product of the matrices or by using Quirk, for instance. And you can see, for instance, that Z can be generated as this product of the Hadamard gate, the NOT gate, and then again the Hadamard gate. Also, the S gate that we studied in the previous lectures, remember that this is a rotation around the Z axis, and it's a rotation of pi over 2. So the T gate is a rotation of pi over 4, so we can do this rotation of pi over 4 2 times to obtain the S gate. And the similar arguments apply to the other equivalences that we have here. So this is an interesting and quite easy exercise to notice that, well, in fact, from a reduced set of gates, we can generate all the others, at least up to some precision that we fix in advance. In fact, in the quantum computers that we use in practice, for instance, in the IBM Q experience, we have not only the X, H, T, and C0 gates. We have more gates, and they are implemented physically. But for some forms of quantum computation, for instance, when we want to do fault-tolerant quantum computation, it is interesting, it is important to know that we can generate several gates from others, and then maybe those other gates that we can implement physically are easier with the scheme for quantum error correction that we are using. We will talk more about this in the last lecture of the course. Okay, so these are some equivalences that you can prove. There are many others. Okay, and if you want to see a more detailed proof of these universality theorems, you can refer to the books in the recommended resources. Okay. To end up our study of n-qubit systems that you have seen is shorter than we have done with 1-qubit and 2-qubit systems, because all the work that we have done so far now paves the way to understand this in an easier way. I want also to show you that for more complicated gates, you can sometimes do a exact decomposition. For instance, for the Toffoli gate, you can check, this is another exercise that maybe you cannot do by computing all the matrices because you have here a lot of gates, but that you can do, for instance, in Qiskit or with Kirk. You can check that this decomposition here gives you exactly the Toffoli gate, and it only uses 1-qubit gates. In fact, the Hadamard gate and the T gate and its inverse, and C0 gates, okay, 2-qubit gates. So you can check this, and in fact, this is the composition that is optimal in the sense that you cannot do this with less than 6 C0s, okay? And you can check that this is exactly the Toffoli gate by taking into account that here we are using the bottom qubits as the controls, okay? So this is one control, this is another control, and the target will be the uppermost qubit in this circuit. Okay, so this is all that I wanted to tell you about n-qubit systems. As you see, it's just a simple generalization of what we have studied so far, and now we can start to think big, start to trying to apply this to problems which are difficult for classical computers, trying to use this exponential growth of the number of coefficients that we are using to describe an n-qubit system. Okay, this is something, sorry. This is something that many times is called quantum parallelism, and is one of the main confusions that non-specialists find about popular descriptions of quantum computing. Okay, so if you read a news article about quantum computing, or you are reading a popular science description of quantum computing, many times you find this statement that, well, quantum computers try all the possibilities or these exponential possibilities in parallel, and then they can solve many problems because they can work with all these possibilities at the same time. Okay. Well, this is a statement that we need to clarify a little bit. Okay, so there is a certain truth to it. We could say that there is a superposition of truthness and falseness to this affirmation, but it's not completely true. I mean, it's not completely exact. It is true that one of the main capabilities or one of the main explanations of the power of quantum computing comes from this exponential number of coefficients that we are working with, but that is not all that it's going on in the algorithms that we are going to use. And in fact, by itself is not something that we can use to solve, for instance, very complicated combinatorial problems or NP complete problems or things like that. Okay, so we need to think a little bit about this and to clarify this. Okay, to do that, let me go back to an idea that we have explored at the end of lecture 3 when we studied the Deutsch-Jotze algorithm. Okay, and this is related to some of the questions I have received about these oracles that we use to evaluate functions, to evaluate Boolean functions, and the number of calls that we do with these oracles, and the number of evaluations of the function f. Okay, so remember that in quantum computing, all gates are reversible. Okay, all gates are unitary, so in fact, they are also reversible. So when we compute a function, when we want to compute, for instance, a Boolean function, what we need is something that is reversible. And for instance, the AND gate in classical logic is not reversible. Okay, so we need to add some extra information to the output of the function to be able to invert it, to be able to recover the input information. We can do this, for instance, with this common scheme of using an oracle in which the inputs to the function are kept unchanged, and then we have a special qubit or set of qubits in which we sometimes write or somehow write the answer. Okay, in fact, we XOR the answer with the values that we had previously on those qubits. Okay, so imagine, for instance, that this qubit is set to 0. Then what we obtain here is, of course, the value of f of x, and we can invert this because we can apply again this oracle and revert the transformation that we have done. This is something that we have done in Deutsch algorithm, and we are going to do it again in several of the algorithms that we are going to study today. Okay, so this is the setting in which we can study, or one in the set of the settings in which we can study this quantum parallelism, this possibility of evaluating a function or working with all the values of a function at once. Okay, so let me recall you how to do this, or well, modify a little what we did in Deutsch algorithm to see that in fact we can use these oracles to evaluate the function in all the inputs at the same time. I'm going to start, as always, with a simple case, which is the case in which we have a function which is a Boolean function with only one input. Okay, so we have a Boolean variable as input, a Boolean variable as output. Okay, so what we can do in this case is, for the input of the function, we can use a superposition. We are going to use the edge gate, and we are going to put the qubit of the input in superposition. Okay, so we start with the state 0, 0. We apply the edge on the first qubit, and then it's easy to check that we obtain this state here. Okay, which is a superposition in the first qubit of 0 and 1. Now we apply the oracle, and well, this is a linear combination. The oracle is a linear function, it's a matrix, so it's going to act in each of the terms separately. Okay, and we then add the results, And what we obtain here is, by definition of the oracle, the value of f in 0. And what we obtain here is the value of f in 1. But we have applied the oracle just once. This is important because this is a question that I have received from several people during the week. Okay, notice that I'm using the oracle only once. Okay, and some people were confused because they saw that here we have the function twice. Okay, so it seems that I have called the function 2 times. But this is not the case. What I have done is to call the function once, but on a superposed value, on a superposition. Okay, and because of the linearity, we can express this value as 2 different terms which are combined in this superposed final state. Okay, but I'm only calling the function once. I'm only calling the oracle once, and I'm obtaining the result of the function on the 2 possible inputs. Okay, so I'm doing just one evaluation, but I'm obtaining the result of the 2 possible inputs. Okay, we can do this also with n-qubit systems. Now what we have to do, we will have, of course, n qubits as the input of the function. Now we have a function with n Boolean variables, and what we do is to first use the Hadamard gates to have all these possible inputs in superposition. Okay, and then we are going to use the oracle. So if we apply the H gates to this initial state, which is 0 on all the qubits in the input and in on the qubit that we are going to use to recover the output, you can see that the first qubit is going to be 0 plus 1. The second one is going to be also 0 plus 1 up to the nth qubit. The one for the output has not been modified. And then we have this normalizing factor here. Okay. So this is just the application of the H gate. But if we expand this product here, we are going to obtain all the possible combinations of zeros and ones. Okay, exactly 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, all the possible strings with zeros and ones, because here we have a product of 0, 1, 0, 1, 0, 1 on all the qubits. Okay, so we have this state, which is equivalent to the one that we had here, to the one that we had here, okay? And we can write this in a more compact way, as we have mentioned before, with this sum here. This sum here, it's over all the values from 0 to 2 to the n minus 1, okay? And we have here the value x. Now, if we apply the oracle again by linearity, what we obtain is that in this qubit that someone from the Bogdan Pulpescu, thank you, from the Zoom meeting, tells me that it's called ancillary or auxiliary qubit. In fact, okay, so we obtain in this auxiliary or ancillary qubit the evaluation of f on x. Okay. But we are doing this by linearity on all possible values of x at the same time with just one call, because you see here that the circuit only has one use of the oracle f. So we are doing an exponential number of function evaluations with just one call. Okay, so this is something really very impressive. We are doing, if the number of qubits is 100, we are doing 2 to the 100 evaluations with just one call. Okay, so that is something really, really impressive. Okay, the problem here is, well, we have done this evaluation, supposing that the qubits are perfect and all my gates are perfect, there are no errors. Okay, we will talk about that later on the course. But we have done this exponential number of evaluations. So now what? Now how can I recover some useful information from this? Okay. If we had a non-deterministic machine, maybe some of you have studied the model of non-deterministic Turing machines, then in this situation, we have something similar to this evaluation of all the values of the function at once. In a non-deterministic machine, we have several points in the computation in which we split the tree of computation, and we are following several paths at once, okay? And in the model of non-deterministic Turing machines, or non-deterministic machines in general, then if at least one of the results that we obtain is what we expected, for instance, it's a 1 in the case of a Boolean function, then we can stop and say, okay, the computation has succeeded, okay? So somehow we can choose at will from all those results that we have in the non-deterministic computation. But that is only a mathematical model, okay? It's a mathematical model to study complexities of problems and to relate what we can do with actual classical computers to these mathematical models. This is not something that we can do in practice, okay? Not even with quantum computers, okay? This would allow us, for instance, to select one of these values fx here and to check if at least one of them is 1, and then we could solve NP complete problems. For instance, the satisfiability problem would be trivially solved with this kind of machine, okay? And in fact, if you like science fiction, this is something that is used by one of my favorite science fiction writers, the Australian Greg Egan, in this novel, Quarantine, nothing to do with the current lockdowns and quarantines that we are experiencing. This is back from, I guess, 1992 or something like that. And in the plot, a very interesting and convoluted plot, he uses this possibility of having a superposition of different states, quantum states, and selecting one of them. I don't want to spoil too much about the plot in case you haven't read it, but it's related to this situation, okay? So in a non-deterministic machine, or in this novel, we could somehow choose the answer that we want, but in practice with quantum computers, even if we have potentially evaluated or actually evaluated, and we have potentially all the information about the result on the function on all the possible inputs, we cannot select one of them just by will, okay? What we need to do, remember, is to measure this. But when we measure a state like this one here, this is going to collapse in one of the possible situations, in one of the possible states of the superposition. And the state that we are going to obtain is going to be completely random. And all of them have the same probability. All of them have probability 1 over 2 to the power n, okay? So we are going to obtain, when we measure that, we are going to obtain just the evaluation of the function on one point, on one input, and completely at random, okay? So this is something that is even worse than what we had in the classical case, because in the classical case, at least we can select on which input we want to evaluate the function, okay? So just by itself, the possibility of creating this impressive superposition here is not helpful. This is something that we cannot use directly. What can we do then? Well, remember that we have always talked about 3 different properties of quantum systems that are the heart and soul of quantum computing: superposition, entanglement, and interference. And here we are using, of course, superposition. We are using entanglement because each value is entangled, or each input is entangled with its output, okay? But now we need to use also interference in order to obtain from this combination of different values of the function something that is useful for our computations, okay? I strongly recommend that you read this comic by Scott Aronson and Zach Weiner-Smith that I have taken the liberty of representing here with some of the pictures, okay? In which, in a very funny but also very informative way, they explain how quantum computing is not only about the possibility of doing this quantum parallelist evaluation and this superposition, but also, and even more importantly, about the interference that we need to create to somehow annihilate those amplitudes of the answers that are not interesting for our problem, and at the same time to make the probability of the answers that we need to be bigger, okay? And this we can do because the amplitudes are not probabilities, they are complex numbers. So they can be negative and they can either reinforce or negate one another, okay? And this is something that it's not easy to do, but we know how to do it in several interesting, important cases. And this is what gives rise to these quantum algorithms, these famous quantum algorithms that we are going to study, okay? So very important, not only quantum parallelism, not only superposition, but interference is also the key ingredient of these quantum algorithms. And we are going to see that in practice now, okay? Any question up to this point? Okay, so let's study one of these quantum algorithms, what is called the Deutsch algorithm, which is a generalization of this Deutsch algorithm that we studied last week. So just a quick reminder of what we did. Remember that we had this problem in which we were given an oracle for a Boolean function of one variable, and the problem was to determine whether it was a constant function or a balanced function. A constant function is one that always returns the same value, always 0 or always 1, while a balanced function returns 0 for one of the inputs and 1 for the other, okay? And these are all the possibilities that we have with a one-bit Boolean function, okay? Either it is constant or it is balanced. And we used this circuit here on the bottom of the slide to answer this question in the quantum setting with just one call to the oracle of the function, with just one function evaluation, okay? One quantum function evaluation, but as we have mentioned before, with an input in superposition. And this is something that in the classical case would need two evaluations of the function, because if we evaluate the function on just one of the inputs, it's impossible to know whether it is constant or it is balanced, because on the other input it can be the same or a different value, okay? So we can generalize this to a situation in which we have functions with more than one input, okay? Now we are going to have, again, a Boolean function, but with n variables, with n inputs, okay? And again, we are going to check whether the function is constant or the function is balanced, and this is defined exactly as in the case of the one variable Boolean function of Deutsch problem. A constant function is one that returns always 0 or always 1, while a balanced function in the n variable case is one that for half of the inputs, that is 2 to the n minus 1, it returns 0, and for the other 2 to the n minus 1 returns 1, okay? Notice that this does not include all possible Boolean functions. There are many Boolean functions which are not constant, neither constant nor balanced, okay? In the case of one variable, all functions are either constant or balanced. That is Deutsch's problem. But now, not all Boolean functions of n inputs are constant or balanced, okay? So what we have here is what we call a promise problem. A promise problem is one in which we are not given a general input, in this case, a general Boolean function, but one that is selected from a reduced set of inputs. In this case, the function is going to be either constant or balanced. So we are promised that we are given this oracle and it implements either a constant function or a balanced function. Okay, and we don't know which is the case, and we need to determine by evaluating the function as few times as possible if the function is constant or it is balanced. Okay, it is easy to see that if we use a classical deterministic algorithm, sorry about that, we need to evaluate the function on at least half of the inputs plus one. Okay, because if we are very unlucky and the function is balanced, but we always select values on which the function is zero, for instance, okay, half of the inputs are zero. So imagine that half, the first 2 to the n minus 1 points in which we evaluate the function give us zero. This is compatible with being the constant function that always returns zero, but it is also compatible with being a balanced function that happens to be zero exactly on that number of inputs, and it's one on the rest. Okay, so we need to evaluate the function on at least half plus one of the inputs, and this is an exponential number of different possibilities. Okay, what we are going to do is to solve this problem with a quantum algorithm, evaluating the function just once. Okay, so we are going to reduce the number of calls from 2 to the n minus 1 plus 1 to just once. Okay, and this is impressive, although we will later on discuss what is the significance of this result for practical tasks. Okay, so how to do this? What we are going to do is to generalize the algorithm or the circuit that we used for the Deutsch problem, and we are going to use a very similar circuit, which is this one here. And notice that the only thing that we have done here is to extend the number of qubits, because now we have more qubits on the input. We keep the auxiliary qubit in state 1, and the rest of the circuit is the same, and we measure in these qubits on the top. Okay, so how to use this and why does this work on the problem that we are posing? Okay, so let's see what are the different states that we obtain when we used an oracle for a function that is either constant or balanced with the circuit of the previous slide. Notice that we start with the state that on the inputs is 0, and on the qubit for the output is 1, okay? And then we use Hadamard gates to create a superposition. We already know that if we apply Hadamard gates to this part here, we obtain the superposition of all the possible strings, okay? So these are all the possible strings on n qubits, okay? And then if we apply the Hadamard gate on this qubit, which is in state 1, we obtain the minus state, which is this one here, and then we collect all the normalization factors in this coefficient here. Okay, so this is something that we have already done, and we know that this is the state that we have. Now we apply the oracle, and the oracle, as always, is a linear function. It acts linearly, so we can evaluate on each of these products by itself, and we know that for x, it is going to XOR here f of x in the case of this qubit being 0 or this qubit being 1. So we obtain 0 plus or XOR fx, 1 XOR fx, okay? But remember from Deutsch's algorithm that fx is either 0 or 1. If it is 0, then this does not change. 0 XOR 0 is 0, 1 XOR 0 is 1. And if fx is 1, then we are going to invert. We are going to change 0 to 1 and 1 to 0. So what we are going to have is 1 minus 0, okay? And we can write all this in a more compact way by using this factor here, -1 to the power f of x. Because if f of x is 0, then this is 1, and we have 0 minus 1, which is what we needed. And if f of x is 1, then we have -1, which is multiplied by this 0 minus 1 is 1 minus 0, as we needed, okay? So what we are doing here, as we mentioned last week, is to use this state to introduce a phase of either -1 or 1, depending on whether the function on that point is 1 or 0, okay? Now, what can we do with this? Well, remember that we are going to apply a new column of Hadamard gates, and then this is something that you can compute. I'm not going to do this derivation here because it's quite easy, but it's also very long, so you can try this to apply the Hadamard gate, the column of Hadamard gates to a general string X, okay? And you will obtain that the new state is this double sum that we have here, okay? So we still have the phase that was introduced by the oracle, and now we have a different phase that is introduced by the second column of Hadamard gates. And we have here, what we have here is just the inner product of the strings X and Y. These are binary strings. And what we do to obtain, to compute this inner product is just to multiply the corresponding bits, 0 times 0, 1 times 1, 1 times 0, whatever. And then we add all the results, the usual inner product, okay? And you can check that, in fact, the Hadamard gate introduces these phases according to this inner product here. Okay, so this is something that you can check. It's a mildly long computation, but it's not difficult. Okay, and then remember that what we do is we measure the first 10 qubits. Okay, with the circuit. What do we do with the result? We compare the result to the string that is this is incorrect. I should change this. Sorry about that. I will change the other error and this one. Okay, so this should be different. I copied this from the Deutsch algorithm. So this should be different from 0. Okay, so we are going to compare this result to 0. If the result is 0, then we can be sure that the function was constant. If the result is different from 0, then we can be sure that the function is not constant. And then, since the function was either constant or balanced, then we are sure that the function is balanced. Why does this work? Why is it enough to compare this result that we obtained to 0? Well, we can easily see this by computing the probability of obtaining 0 when we have this state here. Okay, so we have this state here. What is the probability of obtaining 0 if we measure? Well, it has to be the amplitude squared of the coefficient that goes with the string 0. Okay, so we can substitute here 0, and we see that we have this coefficient here with y equal to 0. Okay, so this is exactly what I have computed here, and then we square that. But since y is 0, this factor here reduces to 0, and we have this sum here squared. Okay, which only depends on f, and on its values on all the possible strings x that we have evaluated. Okay, but now notice that if f is constant, then this value is always 0 or always 1. So this value here is always 1 or always -1. Okay, and since we are squaring this and we are summing over 2 to the n possible binary strings, what we obtain, either if the function is always 0 or either if the function is always 1, is 1 for this probability. So the probability of measuring 0 if the function is constant is exactly 1. We will always obtain with certainty the result 0. However, if the function is balanced, then half of these values are going to be 0, half of these values are going to be 1. So half of these coefficients here are going to be 1, half of these coefficients are going to be -1, and 1 is going to cancel another. Here is where we find the destructive interference. In the other case, we were obtaining constructive interference, but here some of the amplitudes are annihilating with others, some of them are canceling others, and the probability of measuring 0 when we have a balance function turns out to be 0, okay? So it is enough, as we mentioned in the previous slide, to measure all those top qubits and to compare the result with 0, with the string which is all zeros. If the string is all zeros, this can only come from the fact of f being constant. If the function is, if the result is different from 0, this can only come from the fact that the function is balanced. Okay, so this is why we solve this problem. It's kind of magical, okay, but we are, notice that what we are doing is, in fact, interfering a lot of different amplitudes to make them cancel each other, okay? So this is the statement of the problem, the solution with the quantum algorithm. Let me give you some comments on this, and then we are going to run an example of this algorithm in an implementation in Qiski. So first of all, of course, this is a problem that it's clearly artificial. This is something that was fabricated especially to show this potential of quantum computing. Okay, this is not a problem that is of practical interest. There is no natural situation in which we are given a Boolean function, which is either constant or balanced, and then we need to evaluate which is the case. There is no simple situation in which this arises. Okay, but it's an interesting example. It was one of the first quantum algorithms that was proposed, and an interesting example of how to use that quantum parallelism, that exponential potential of quantum circuits to do something that for classical computers would be hard, would be much more difficult because they would need much more evaluations of the function. Okay, and as I have mentioned, and this is very important, we are using the quantum parallelism together with interference. This problem is also interesting because similar ideas were used subsequently to define other algorithms, other problems, and other quantum algorithms to solve them. For instance, the Bernstein-Basirani algorithm, which you can find in the books on the recommended resources, and the Simon algorithm. I'm not going to go into detail into these algorithms because, well, are similar to the one that we have studied and are also not very practical. But these algorithms were also interesting in the historical development of quantum computing, especially Simon algorithm, because it was the inspiration for the famous Shor algorithm that we are going to study maybe at the end of this lecture or at the beginning of the next one. Okay, so the ideas that these researchers were working with these problems there were then useful for other more practical algorithms that were defined. Okay, also I want to mention that here at Open Lab, we have been working and we are finishing a draft on a paper with a generalization of these Deutsch-Judson, Bernstein-Basirani algorithms. So, well, this is something that it's also interesting, I think, today from the point of view of the theoretical foundations of quantum computing and to try to give a better understanding of why quantum computers can do some tasks faster than classical algorithms. Okay. Any question about this? Okay. So, well, I encourage you again to try to check all the computations that I have skipped here in order to see how this algorithm works. It's not intuitive. It's sometimes difficult to see what is going on, but at least if you reproduce the computations, you can be sure that everything is working properly, and you can gain a deeper understanding of what is going on with these circuits. Okay, so let me then go to the IBM quantum experience. Okay, where I have already, oh, what is the problem here? Let me try again. Okay, it seems it's working. Okay, so I have already uploaded this notebook for the Deutsch-Jotza problem, which you can find on the Indico page. So please, if you want to test it now, go to the Indico page, download the notebook and upload it to either the IBM Quantum Experience or to your local installation of Qiskit. Okay, so let me show you what I have done here. And as always, I will also not only implement the algorithm with the instructions and the techniques that we have seen so far, but I will also introduce some new operations that you can do with circuits in order to work more in a more comfortable way with Qiskit. Okay, so the first thing that is different, I think we used this the other week. We divided our circuit in different registers. Okay, if not, or if you don't remember, I'm not completely sure. Let me explain very quickly that what we are doing here is to first create several qubits as a somehow individual unit, what we call a quantum register. We give that register a name, in this case Q for the input, out for the output, and then we also declare some classical bits in order to make the measurement. Okay, notice that we only need the same number of classical bits as the number of variables in the input of the oracle, because we are not measuring the output. The output is only used to introduce this phase in the algorithm. Okay, and from those registers I create a quantum circuit. Okay, now we are working with a number of qubits that is variable. In this case, well, I'm setting it to 4, but you can change this number. So it is convenient to introduce the Hadamard gates not one by one, because then we would need to fix a number of qubits, okay? But to do it depending on this number with a for loop, okay? So what we do here is to introduce a Hadamard gate for each qubit. And then we apply the initial NOT to the state of the qubit for the output, because we need it to be in state 1, and then we apply the Hadamard gate. And we create this barrier, which is just a something that helps us to separate one part of the circuit from another when we draw the circuit. This is nothing that has any effect on the operation of the circuit. Okay, I should have run this before, because now it will take some time to load the packages and to draw this. Okay, but I will explain the following cell and then we go back. Oh, okay, it's now here. Okay, so you see here the Hadamard gates for the inputs, the NOT gate, the Hadamard gate, and then the barrier to separate from the other part. Okay, now what I'm going to do here is to create a new part of the circuit, which is the one in which we are going to apply the Hadamard gates and the measurement. Okay, and this is what I'm calling circ end. Again, it acts on the same registers, and it has this barrier to separate from the previous part, and then the Hadamard gates and the measurements. Okay, if I draw this, you see that this is the final part of the circuit. Now what we are going to do, and I have separated this circuit into different parts in order to be able to change the oracle that we have in the middle, because we want to test it with a constant function and with a balance function. Okay, so that's why I have defined these circuits in different parts to be able then to combine them with different oracles. Okay, so here I'm going to define an oracle that is always 1. You can do this in several different ways, and you can try your favorite one. But for instance, what I'm doing here is to use a C naught from the first qubit to the output, and then these X gates and the C naught gate from the first qubit to the output. So what this circuit does is, if Q0 is 1, then it is going to add 1 here, okay? And if Q0 is 0, then this is going to do nothing, okay? Because this is a control gate and the control is 0. Then this X gate is going to change from 0 to 1. Then this gate is going to act and invert the qubit here. And then we are going to return the qubit to its original state 0, okay? So if it is and of course, if the input is 1, this is going to be changed to 0, and this is not going to act. Okay, so you can check that if either the input here is 0 or the input here is 1, we are going to flip this bit here. And of course, Q1, Q2, Q3 have no impact on the result. Okay, so the output of this function is going to be always 1. So this is a constant function. This is exactly what we wanted, okay? And I'm also going to create an oracle for, in this case, a function that is balanced, a function that returns 1 on half of the inputs and 0 on the others. And again, this can be done in many different ways. There are many different balanced functions and many different functions, or many different ways of implementing them with quantum circuit. But in this case, I'm just using a C-naught gate, and the effect of this C-naught gate is that if Q0 is 1, then this is going to be flipped, and if Q0 is 0, nothing is going to happen. Okay, so half of the times, and again, Q1, Q2, Q3 have no influence on the result. So half of the times, the result is going to be 1. Half of the times, the result is going to be 0. So this is exactly the balance function that we wanted. Okay, so now what I'm going to do is to create a complete circuit from the initial part, the oracle, and the final part that we have created separately. Okay, so first I do this with the constant function, and you see here the final circuit. This is the initial part, this is the oracle for the constant function, and this is the part in which we do the measurements. Okay, and notice that I can use this very useful operation of concatenation of circuits to create a bigger circuit from individual circuits. Okay, so this is something that is also very useful, and this is, I think, the first time that we use this operation. And now we are going to execute this circuit, and remember that the output of the Deutsch algorithm is, the function is constant if what we measure is 0, the function is balanced if what we measure is different from 0. So here we are using an oracle for a constant function. We are repeating this 10 times, but you can repeat it as many times as you want. So this is going to return 0, a string of all zeros, all the times. If you increase this to 100, for instance, again, you obtain always 0, okay? Because the analysis that we did showed that with probability 1, with a constant function, you are going to obtain the string that is all zeros. Now we are going to create
the circuit for the balance case. And now we are going to run this and see what is the result. In this case, we obtain this string that is not all zeros. Again, if I change this to a bigger number, I always obtain the same result. Well, in this case, I obtain always the same result. For other balance functions, you can obtain different strings each time you run the circuit, but none of them will be zero. Okay, you can obtain different strings, but depending on the balance function that you are using, but none of them will ever be zero. Okay, and then we can conclude, of course, that this function is balanced. This was done with the simulator. Let's do it with the actual quantum computer to see how it goes. Okay, so let me check whether the queue is very long or not to decide whether I wait for the results or I continue with other things and then we go back to see the results. Oh, 32 jobs ahead of us in the queue. So we should rather, oh, it's number 14. Well, I think we should rather do something else and then go back to see the results. Okay, I'm going to run this also to collect the results or to compare the results after we have run this. Okay, so we will see what happens. We expect the circuit to return always zero when the function is constant and always something that is different from zero when the function is balanced. We will see what happens. Okay, any question up to this point? Okay, so let me please go back to my slides. We will check these results later and begin talking about a much more practical quantum algorithm. Up to this point, we have studied these Deutsch and Dot-Joyce algorithms, which are mostly academical. Now we are going to do something that is much more practical, and this is called Grover's algorithm, and this is probably my favorite quantum algorithm, or one of my favorites. I have worked extensively on different applications and modifications and generalizations of this algorithm. So, well, I think it's very interesting, and it's also very different from classical algorithms, but at the same time, it's useful, and there are several different proposals to use this, even, for instance, in tasks in high energy physics. Okay, and you will see in a moment why. Okay, so what is this Grover algorithm used for? Grover's algorithm is used for searching elements in an unsorted structure or list. Okay, so imagine, for instance, I like to give always this example because I think it's very clear. Imagine, for instance, that you have a phone book, old-fashioned paper phone book, okay, in which you want to find a person, but you only know his or her phone number. Okay, so this phone book, of course, is sorted alphabetically, but is not sorted by phone number. Okay, and what you have is the phone number, and you want to know the name of the person. What can you do in that case? Well, in the classical case, there is not much more option than just starting to read the book at some point, or to check some of the entries at random until you find the number that you wanted, and then you recover the name. Okay, so this is the situation in general when you have an unsorted list of elements and you want to find one of them that satisfies a certain condition that is interesting to you. In the general case, this is not sorted at all. With a classical algorithm, you are going to check in average half of the registers in the list before you find your element. Okay, and there is no other way of doing this, because the element can be anywhere. Can be, if you are very lucky, at the beginning or in the first place that you check, or it can be at the end or in the middle. You don't know, and it's not sorted. You have no additional information to start your search. So if you, for instance, have a list of, let's say, 10,000 elements, you need to check about 5,000. Okay, if you have a list of 1 million elements, you need to check about 500,000. Okay, in the quantum case, with Grover's algorithm, you can reduce the number of times that you need to check the list to the square root of the number of total elements. Okay, so if we have 10,000 elements, in the classical case, we need about 5,000 checks of the list. In the quantum case, we only need 100, which is the square root of 10,000. If we have 1 million, in the classical case, we need to check about 500,000 elements in the list. In the quantum case, we only need 1,000 elements to be checked in the list. Okay, so this is quite a substantial gain over the classical case. Okay, we will talk later about whether this is as good as it seems, or what are the caveats with this algorithm. But well, at least in these situations, it is quite impressive. And for this reason, it has been proposed to be used in situations in which you need to search for information, for instance, in several different tasks in which you have to find elements that satisfy certain conditions. And this can be useful in high energy physics, in which we have these very huge databases of information about collisions of particles, and we need to recover some of them that satisfy a certain condition. Okay, so how does this algorithm work? Well, first of all, we need to translate somehow the information that we have to something that we can use in a quantum computer. Of course, if we have a list, even something that is implemented as a file in a classical computer, or as a data structure in a list structure or an array in a classical computer, this is something that we cannot use directly with these quantum circuits. There is no way of, well, reading a file, so to say, with the quantum circuits that we are using. So what we are going to do is to assume that, again, as in the case of Deutsch-Jozsa's algorithm, we have an oracle. And this oracle is, again, a Boolean function that is going to return 1 when the element that we are checking satisfies the condition, and 0 when the element that we are checking does not satisfy the condition that we are interested in. Okay, and this input here can be the index of the element in the list, for instance. Okay, so we have a number for each of the positions in the list, and then we feed this number in the oracle, and the oracle says 0 or 1 depending on whether the element satisfies or not the condition. Okay, so this is what we assume. To implement this in practical situations, we would need a way, for instance, of querying a file or some data that we have in digital form in superposition, and this is something that we are going to talk about in more detail when we talk about quantum machine learning. So this is maybe a technological problem, but let's assume that we have this oracle, and that when we feed it with an index of one of the elements, it can return 0 or 1 depending on whether it is the element that it's not the element that we want, 0, or it is the element that we want and it returns 1. Okay. Then what we are going to use is, of course, we are going to do interference. We are going to use all these properties of superposition, of course, entanglement and interference. And what we are going to do is to manipulate these amplitudes with an idea that is called inversion about the mean. And it's the main idea behind this algorithm. So imagine that the element that we want is the one that corresponds to this red bar here. Okay. So this is the original amplitude of the element. Of course, at the beginning, we are going to use an equal superposition, as we always do, of all the elements. So at the beginning, all the amplitudes are the same. Okay? And we cannot know just by that big superposition what is the element, because this is the situation we were talking about when we discussed quantum parallelism. Of course, we can evaluate the function, and then some of these values will be 0, some will be 1, but we cannot select an element with value 1 just because we want. We need to do something with the amplitudes in order to select it. Okay? So what we are going to do is to use this trick of the phase kickback that we used in Deutsch and Deutsch-Jotz's algorithms, in which we introduce this -1 to the power f of x. And if the element is the one that we are searching for, then this is going to introduce a phase of -1 in front of the amplitude of this element. And this is what we call here negating the amplitude. So the amplitude is going to be the same one, it's going to have the same magnitude, but now it's going to be negative. And now, and this is the neat trick of Grover's algorithm, what we are going to do is, with a unitary transformation, we are going to compute the average of all the amplitudes. This average now, it's a little bit less than it was before, because one of the elements now is negative. At this point, it was all the elements were equal, so the average was the value of any of them. But now one of them is negative, so this is going to be a little bit lower. And then we are going to flip all the amplitudes around this mean. That is why we call this inversion about the mean, because we are doing a reflection around this mean. Okay, and then of course the ones that are above are going to be a little bit below, and the one that was much more negative, that one that was below the mean, it's going to come on top. Okay, this is clearly exaggerated in this case, because in the general situation we are going to have 2 to the n elements, and we are only reducing the average a little bit when we flip one of the amplitudes. But in the end, after several iterations, this is going to add up. We repeat this several times, and then the elements which are not the ones that we want are going to to gradually reduce their amplitudes, and the one that we are searching for, it's going to have a very high amplitude. Okay, so this is the idea. How do we do this? How do we do this with a quantum computer? Of course, you can do this with a classical computer, but then you need to iterate over all the values. So it's not good, because, well, you might as well just check which of these values is -1 and then you select it. Okay, so this is not something that is helpful, although you can do it in the classical case, because then you need to operate over all the values and you do not reduce the complexity. Okay, so how do we do this in the quantum case? In the quantum case, what we do is to use this circuit here, which, as you can see, it's somehow similar to the one that we used for the Deutsch-Jotz's algorithm, because in fact, this part here of negating the amplitude is exactly what we did in the Deutsch-Jotz's algorithm. We just introduce this -1 phase. Okay, so the first part is the same. At this point, we are introducing this negation of the amplitudes of the element or elements that we want to find. And then we have this part of the circuit here, which is what it's called Grover's diffusion operator, which is the one that computes this average and computes or performs this inversion around the mean. Okay, and we need to repeat this a number of times, which is proportional to the square root of the total number of elements in our list. Okay, so you can just take this circuit and study the unitary matrix that corresponds to this part, to this diffusion operator, and you will obtain that, in fact, what it is doing is this inversion around the mean. This is you can find this in several of the textbooks that I have included in the recommended resources. And this is a possibility to study this algorithm to see why it works and the number of times that you need to repeat this. But I prefer a different approach. I'm going to adopt the approach that you can find in the very fine lectures by John Watrous that I have also included in the recommended resources. Okay, and what he does is to interpret Grover's algorithm as a rotation. In fact, if you are good with geometrical interpretations, I'm not at all, you can see that, well, this is a reflection and this is again a reflection. This is quite easy to see. And then you have a composition of two reflections and this is a rotation. To me, that is in a high dimensional space, very difficult to see. If you can see that, well, this can help your intuition. But the idea is that even algebraically, you can show that the operation that we are doing here is in fact a rotation. And we are going to compute what is the angle of rotation and how that it helps us in determining the number of times that we need to repeat this operation of the oracle and the diffusion operator. So what we can do to see that this is a rotation, I'm not going to give you all the details, just the ideas. You can check them, and I think it's a very interesting read in John Watrous' lecture notes. What we do here is to separate the initial state. Of course, the initial state is an equal superposition of all the different elements. This is something that we have repeatedly used today. This is the first step of all our quantum algorithms, okay? But now we are going to write this in a different way. This equal superposition of the initial of the upper qubits, the input to the function, we can write it as a combination of the element that we are searching for and the rest of the elements. Okay, so here this x0 is the superposition, the uniform superposition of all the elements that are different from the one that we are searching for. Okay, or you can write this in a different way by saying that these are the elements on which f gives the value 0. Okay, and x1 is the only element on which f gives the value 1. Now notice, well, you can easily see that this is exactly the same expression that we had before, because this n-1 cancels with this n-1 here. We are writing the same state in a different way. But now notice that this value, this square root here and this square root here, when we compute their squares and add up their values, of course, they add up to 1. So this means that I can write this square root here, this square root here, as the cosine and sine of an angle that is between 0 and pi over 2. Because, of course, these values are between 0 and 1. Okay? So let's define theta to be the angle such that the cosine of theta is this square root and the sine of theta is this other square root here. Now, if we study the unitary transformation, that is the composition of this oracle and this part of the circuit, this diffusion operator, then we can easily see, well, not so easily, but it's just algebraic manipulation. You can find this on John Watrow's lecture notes, very well explained. You can find that, in fact, this is acting like a rotation of angle 2 theta on the two-dimensional space that is spanned by x0 and x1. So now I consider just the two-dimensional space that is formed by the vectors that are combinations of x0 and x1. And if I consider the action of this operator, I can see that it acts as a rotation of angle 2 theta. Okay, here you have the complete expression of that rotation. But the idea is that I'm going to, every time that I apply this operator, I'm rotating the state by this angle 2 theta. So if I apply the rotation m times, if I apply this part of the circuit, oracle plus diffusion operator, m times, I'm going to increase, because the initial state is as we had rotated angle theta from x0, what we obtain is a rotation, a total rotation of angle 2 times m plus 1 theta. Okay, the initial rotation that we had in the initial state, in this one here, plus the m times that we have rotated by angle 2 theta. Okay, and now what we want is this value, this amplitude here, to be close to 1. We want to stop after doing a number of iterations that makes this value here to be close to 1, because then if we measure at that moment, we are going to measure x1 with a high probability, and that is exactly what we want. So we only need to solve for m here. This is the number of iterations that we want to do. In order for this angle to be close to 1, for this sign to be close to 1, this angle here needs to be close to pi over 2. So we make this approximately equal to pi over 2. In general, we cannot do it exactly pi over 2 because this is just an integer and we have no a continuous range of values, but we want to find something that makes this close to pi over 2. And then just by doing some algebra, we obtain that this is close to pi over 4 theta minus 1/2. Okay, but since this sign here of theta is 1 over the square root of 1 over n, and n is big because in general we are using a lot of elements here, and remember that the number of elements is 2 to the number of qubits. Okay, that is the number of strings we are searching over. This is going to be very close to 0. Okay, so we will have that this sign in fact is very close to theta. So we can go here and substitute theta with this value here, and well, truncate or round this value to the closest integer and obtain the number of iterations that we need, which is going to be the closest or the ceiling of this pi over 4 times square root of n. Okay, so the number of iterations, the number of times that we need to check the oracle, because each time that we apply this diffusion plus oracle operator, we are using one call to the function, is of the order of the square root of n. Okay, and this is how we prove that we have this quadratic speedup over the classical case. Of course, this is for the situation in which we only have one marked element, one element that is that satisfies the condition that we are interested in. But we can study this also in the case of multiple marked elements, when we have many elements that satisfy the condition. Now what we do is to separate again, the initial state into a part which is x0, the elements that are not marked, the elements that are not, that do not satisfy the condition, and x1, the elements that satisfy the condition. Again, we do this identification of values with sines and cosines. We see that this is again a rotation, but in this case, the angle is the number of marked, the square root of the number of marked elements, which in our previous case, of course, was 1 over n. And then we obtain something that is the number of iterations that we need to do is the square proportional or very close to the square root of the total number of elements divided by the number of elements that are marked. So again, a quadratic speed up, okay? There is something that you may be wondering here, and it is that, well, in order to determine this number of iterations that we need to do, it seems that we need to know k. In this case, explicitly, in this case, because we are assuming that there is only one marked element, one element that satisfies the condition. What happens if we do not know the number of elements that satisfy the condition? That is the more general situation, the most general situation. We are looking for an element that satisfies the condition, but we don't know how many of them there are in our list. Okay, in that case, we are also covered. We need to slightly modify the algorithm, but we still can obtain this quadratic speedup. There is no problem with that, because what we can do is to adopt one of two strategies. The first one is to use something similar to this algorithm for this circuit for Grover's algorithm, together with the quantum Fourier transform that, well, I see that today we are not going to be able to cover, but we will cover first time next week, to estimate k. And then we can use regular Grover with this estimation of k. Or we can use a modification of quantum of Grover's algorithm, in which we select the number of iterations that we do with this oracle and diffusion operator uniformly from this set here, okay? Or we select the number of iterations starting with 1 and then exponentially increasing the number of iterations up to the square root of m. The analysis here is a little bit more complicated, but again, it uses this expression of the state that we have after m iterations, and you can find all the details in the books, or if they are not there, just ask me. I can point you to some quite readable research papers in which this is explained. But even if you don't know the number of elements that are marked, you can recover this quadratic speedup. Okay, so this is not something that you should worry about, and this is something that, for instance, I have done with my research team back at the University of Oviedo for several different situations. For instance, for some algebraic problems in which we are interested, and this works in practice. If you have a powerful and precise enough quantum computer. Okay, so just some final comments before running this algorithm, if you don't have any question up to this point. First, notice that we are going to obtain a measurement from this Grover's algorithm. And since we have some probability, depending on the number of iterations and the number of marked elements that we have, of finding an element verifying the property, and some probability of not finding this element, this is an algorithm that is not like Deutsch-Jotz, in the sense that maybe we need to repeat this algorithm several times. We can certify or we can guarantee that we will obtain the solution. For instance, in these cases in which we do not know the number of marked elements, we can give a lower bound on the probability of success, which is, if I remember correctly, like 0.25 or something like that, which may seem not very much, but if you repeat this algorithm, for instance, 10 times, then the probability of obtaining a marked element is very high. Okay, so this is something that you need to take into account. This is not like Deutsch-Jozsa. You are not going to obtain the correct result every time. It is completely probabilistic. Okay, and also because of this dependence on the number of marked elements and the number of iterations, you need to be very careful in how you select the number of iterations. And this is something that it's not very easy to understand if you think about, or if you try to compare this with classical algorithms. Of course, if you have a classical algorithm, the more times you check the list, the most probable it will be that you will find the element. It's completely logical. I mean, if I check more places in the list, I have more opportunities of finding the element. In Grover's algorithm, this can be completely wrong. I mean, if you check too many times, maybe you reduce the probability of finding the element back to 0. Because remember that you are doing a rotation. So if you rotate the element or the state up to a situation in which you have a very high probability of finding the element, that is very nice. That is very good. You are going to measure and have a high probability of finding the element. But if you go on and keep on rotating, you are going away from that situation in which you had a high probability of finding the element. We are going to see this in the execution of the algorithm in Qiski. Okay, but this is something to take into account. Also, for instance, if the number of elements that are satisfy the condition, the number of marked elements is exactly 1/4 of the total number of elements, with just one iteration, you are going to find the element with total certainty. And you can find that just by substituting here on these expressions the numbers that I mean the k and the m in this expression here, and checking which is the angle and why with just one iteration you go up to probability 1 of finding the element. Also, there are different modifications of this algorithm or applications of this algorithm in other settings. For instance, there is this famous Durr-Hoyer's algorithm for finding extremal values of functions, minima and maxima of functions. I'm not going to go into detail into this, but you can use Grover to define this algorithm. Also, what is called amplitude amplification. You can search for that. There is information in the books. It's also the same idea, but with a different, a slightly different transformation. And also something that is very interesting is that, well, you can prove that there is no quantum algorithm that does better than Grover in this kind of problem, in the sense that you cannot obtain a speed up that is, for instance, cubic or better than quadratic in general. Okay, and this can be proved with several different methods. For instance, you have the adversary method, but also you have this polynomial method that you can find in the lectures by Ryan O'Donnell that I have linked in the recommended resources. And I think it's a little bit complicated. It takes like 1 hour to explain fully, but it's also very well explained by Professor O'Donnell, and I think it's worth watching it if you are interested in this kind of proof. Okay? Any question up to this point? Okay, so I'm sorry I do not have time to introduce Shor's algorithm. I will do that first time next week, but I want to go back to QuizKit and run an implementation of Grover. Okay, well, so first of all, this has the Deutsch-Jotze algorithm has finished here. And notice that now we do not have for the constant function always the result 0. This is because of errors in the computer, noise, problems with the measurements, problems, errors in the application of gates. But notice that the most probable solution is 0, 0, 0. Okay, while here the most probable solution for the balance function is something that is not 0. Okay, so even in this case in which you have mathematically proved that the probability of obtaining a certain result is 1, when you use these algorithms in a real quantum computer, you might want to run your circuit several times, because the errors, the noise can make these algorithms to give incorrect results some of the time. So you need to run them several times and, for instance, keep the most frequent solution. Okay, so this is something that I wanted to show you because it's something to take into account when you are doing practical applications in real quantum hardware. Okay, so let me go then to, let me close this and go to my implementation of Grover's algorithm. Okay, so I only have a few minutes. I'm going to run all this very quickly. Okay, so what I do here, the initial part is exactly like in Deutsch-Jotze algorithm. The only difference here is that I'm creating a function to define the circuit, and then I return the circuit. Okay, it's a different way of doing it. I also create a function for the diffusion operator. The diffusion operator has these Hadamard gates, then these X gates, and then it has a multi-control set gate. To implement that, I'm using here a multi-control rotation around the set axis, using, of course, angle pi, okay, which is equivalent to a set operation. And then again dx, again dh. Okay, so I also define an oracle which returns 1 only if all the inputs are 1, because I want to have a situation in which only one element satisfies the condition. Okay, so only one element will return 1 on this oracle. And to do that, I'm going to use a multi-control X gate. So this is a generalization. Sometimes it's called also a generalized Toffoli gate. It's a generalization of the Toffoli gate that we have studied. So it's a X gate, a NOT gate with many qubits controlling it. Okay. And then I define this Grover circuit in which I first use the initial part, just the preparation of the initial state. And then for a number of iterations, I use the oracle and the diffusion operator, the oracle and the diffusion operator, okay? And at the end, I perform this measurement. So what I'm going to do here is first to draw the circuit, which is similar to the one that we had on the slides. You can check that. And then I'm going to run this on, this is for just one iteration of the oracle and the diffusion operator. But since I'm working with a function that has 2 inputs and there is only one element which is marked, we are exactly in the case in which 1/4 of the elements are marked. 1 of the 4 elements is marked. So we know that with just one operation, with just one iteration, we are going to obtain the correct result, which is, of course, 1, 1, which is the only case in which the oracle returns 1. Okay, and this is, in this case, perfectly correct in all the iterations because just one of the 4 elements is marked. Okay, what I'm going to do here now, I'm going to run it because it takes a little bit of time, is to represent the probability of finding a marked element in a situation in which I have an input of 4 elements. Remember that the last one is for the output. So the oracle receives 4 variables. And the maximum number of iterations that I'm going to do is 20. And I'm going to do a range of iterations starting from 0 to 20. Okay? And I'm going to see what is the probability of finding a marked element if I do that number of iterations with Grover, for this case in which I have 1 element marked out of 16. Okay? You can check the code here, but it's nothing special. I mean, it's just computation of the probability of finding a marked element. And you see this very interesting graph here that gives the probability of finding the marked element against the number of iterations. And you see that for this point here, which is 3, for 3 iterations, which is close to the theoretical value that we had derived in the slides, we obtain a probability that is very high. Okay? But then if we do more iterations, we go back to something that is close to 0. And again, if we increase, we go back to a very high probability, but then we go back to 0. So this is why I was telling you that it is very, very important to determine the number of iterations that you need to do, because if you do too much, you can end up with something that is has a probability very close to 0 of finding the marked element. Okay, so if you do not have any question, that is all for today. I want to thank you again for your attention, and we'll meet again next week. Thank you very much.